and welcome back. In the last episode, we talked about the sequencer, which by the end of the episode was happily sequencing. And now we're moving on to the incrementer. I guess my hope is that it's going to happily increment by the time we're done. So I'll start off as I always do with the question, why do we need an incrementer? Starting with our overall architecture diagram, we're going to focus in on the incrementer and the program counter. And for the purposes of this explanation, I'm going to portray the incrementer and the address bus as 8-bit. The purpose of the incrementer is as the name implies. It picks up whatever value is on the address bus and it adds 1 to that value. And note that at this point, that's all it's doing. The incrementer is not storing the value anywhere. It is just happily incrementing whatever is on the address bus. Now I've included the program counter register as part of this diagram because both the incrementer and the program counter register work in tandem and are a critical component to what's commonly known as the instruction fetch cycle. When the load increment register control line is activated, whatever value is in the incrementer is stored in the increment register. And when the select increment register control line is activated, whatever value it contains is placed on the address bus. And note that because now there's a value on the address bus, the incrementer is automatically picking up that value and adding 1 to it. But that value is not being stored anywhere and is not relevant to our next steps. The next step in the fetch cycle is to load the program counter with whatever value was just placed on the address bus. And now we've effectively loaded the program counter with the memory address of the next instruction that needs to be executed. And once that's done, we need to advance the program counter so that the computer can pick up the next instruction. And to do this, we select it to the address bus, where the incrementer will automatically advance that value by 1. We then load the increment register with that new incremented value. And finally, we select that value from the increment register to the address bus and pick it up on the program counter. And this process repeats over and over for every instruction that needs to be executed in our relay computer. So now that we know the purpose of an incrementer, let's talk a bit more about how this binary-based addition would be accomplished using nothing but relay logic circuits. In binary math, 0 plus 0 equals 0. 0 plus 1 equals 1. Now in decimal we know that 1 plus 1 equals 2, and that is true in binary. It's just represented differently. And this logic can be represented in a truth table, and in this case, it's the truth table for a half adder. A half adder consists of 2 inputs, and these are represented by the 1 plus 1. When both inputs are 1, the output sum will be 0. But while the input is 1 and 1, the carry will be a 1. And this represents our new value of 1, 0. I've created a prototype board version of a half adder circuit, and this circuit I've landed on just based on scouring the internet for half adder circuits for relays. So by no means did I invent this from scratch, but I did pick a design that just seemed to resound with me. And the half adder is probably one of the most fundamental circuits that you'll be doing with relay computing. And it really consists of, in this case, 2 DP-DT relays, 2 inputs, and 2 outputs. And these inputs correspond to A and B in our truth table for half adder circuit, as well as our sum out and our carry out. So when the switches are not selected, that would represent 0 and 0 input, which has a 0 and 0 output. When I select A, you'll see that I now have a sum output of 1. And if I press B, I also get a sum output of 1. So pretty straightforward so far. But this is where things get interesting, at least as far as half adders are concerned. When you have both A and B pressed at the same time, you will now see that the carry out is lit. So right now we have 0, 0 equals 0, 0, 1, 0 equals 1, 0, 0, 1 equals 1, 0, and 1 input is a 0 to the sum and a carry of 1. So let's look at how we're going to use half adders to build our incrementer circuit. This simple half adder can add 2 binary digits together, leaving us with a sum and a carry. We can add another half adder and tie the carry out from the first one to an input line on the second one. And this would effectively allow us to represent a 2-bit output. And following the same chain of thought, so to speak, we can add as many half adders as necessary to represent the number of bits needed. For our incrementer, the input lines are all connected directly to the address bus. If we supply a constant voltage to one of the inputs on the first half adder, this will create a ripple effect that will carry through all of the subsequent half adders and increment every input value by 1. So this is a quick demonstration of the ripple carry effect between half adders. These are 2 identical half adder circuits, and what I've done is tied the carry out from the first half adder to one of the inputs on the second half adder. And when I select the A input, you'll see that we get the expected sum value in the first half adder. And if I select the A input on the second half adder, you'll see that you have the same effect. Now, if I select A and B, we have the carry out being activated, which now activates the input on the second half adder. So it has effectively carried the value over to the second one. And if I now select the input on the second one, that would effectively have the same effect down the chain of half adders. Now it's time to take my working half adder design and multiply it by 16. I'll also need to create this gating circuit for the LIC and SIC control lines. And last but not least, we have the edge card, the diodes, and the multitude of LEDs needed for this incrementer. All right, so we have the test rig set up. These two buttons and two lights on the right represent the first 2 bits of the address bus. And we only have the first 2 because, well, we only have the first 2 installed in our incrementer. This button represents LIC, which is the load incrementer, and it takes the value from the incrementer and loads it into the internal register. And the SIC is the select of that register onto the address bus. So we'll give it a test. We'll turn it on. And that's actually great because right now we have 0 on the address bus, and without doing anything, it has incremented that to a 1. And now if I set the first bit of the address bus to a 1, it has now incremented that value. So that's great, that's fantastic. And if I select so a 0, 1 on the address bus, it has correctly incremented that value. So now that I have a value, even just that first value in the incrementer, if I do the load to the internal register, it's now correctly populated that value into the register. And the next step would be, and in fact, before I do that, let me just load something else so we can see that it loads more than one value. And now if I do the select, well, that should be lighting these ones here. It should be pushing the values back to the address bus. So I'll have to do some research and see what's going on. So after a little bit of panic and then some research, I figured out that, of course, I don't have these 2 diodes installed, and these aren't flyback diodes. These are the diodes that will carry that signal through to the address bus. And they're just there to make sure that we don't get any backfeed from the address bus to the relays. So once those are installed, we should see better results. And thankfully, I received my order of diodes that I've been waiting on for weeks. Drum roll. Yes, that is great. So from my perspective, the primary circuits that do the loading and selecting, they're probably the most complicated of everything. Everything else is rinse and repeat. So I'm really confident that if these first 2 bits are working, the rest should. I'm going to go out on a limb and just populate the whole thing, bring it back, and we can start some end-to-end testing. So it wasn't too long before I ran into yet another problem. And this time around, it was with pins 4 and 5. Applying power to those address pins should have activated the relays, but nothing was clicking. After labeling the relays in question, I ran some voltage tests and confirmed that they were in fact receiving what they should be. And only after all of that did I think to flip the board over and see that I had not soldered 2 of the pins. So after a massive facepalm, I soldered up the pins, started up the board, and everything retested perfectly. So it's time to move on with the automated testing. And this round is going to be a bit different than the previous ones. And that's because I'm not only driving signals to the incrementer this time, but I'm also going to be reading them back and confirming that I'm receiving the correct incremented value. The second thing is that I haven't been installing flyback diodes up to this point, and I know that there's been a lot in the comments about that. And that's only because I was waiting for them. They were on back order. So now that I have them, I do want to run the tests before and after installing the flyback diodes, really just out of a curiosity, just to see if there's any material impact on performance of the boards going forward. So that's a wrap on the incrementer card, and that was a lot of fun. I know that there was some boondoggles along the way, from missing diodes to solder joints, but I had a lot of fun building it and I learned a lot along the way. So I'm pretty excited that it's working as expected. And now I'm on to the next card, which is going to be the memory card. And that one is going to pose a whole set of challenges all their own. Mostly because building a memory out of relays would be not only time consuming, but space consuming. And I need to come up with some alternative methods of memory storage while hopefully at the same time finding a balance in terms of the vintage of the technology that you would normally find in a relay computer. So I'm going to have to think about that and think about maybe coming up with 2 separate paths for memory going forward. And on that note, I would love to hear any feedback in the comments from anyone as to your thoughts on what makes an appropriate memory system for a relay computer. Does it matter if it's IC based, or does it have to be really vintage, old school? Would just really like to hear everyone's opinion out there. So until next time, thank you very much for watching, and I'm looking forward to seeing everyone in the next episode.